So we start. We are going to talk about tokenization now. So until now, be it GPT, be it BERT, I have been saying. So what is the date today? 28/03/2024, and we are going to talk about tokenization. So until now I have been, be it GPT, be it BERT, I have been saying we will assume words are my tokens. So until now we have been assuming doing basically tokens equal to words. Now that is not the case. We know what is the vocabulary size for transformers. Anybody remembers? I think it was 37K. 40K, around 40K was for GPT and around 30K was for BERT. Okay. Now, so GPT, including GPT-1, GPT-2, GPT-3, they all use byte pair encoding. Okay. So नहीं लाया मैं वो पेपर. Anyway, so we are going to talk about byte pair encoding. Now, if I basically give you, so for 5 minutes we'll digress from what we have been doing, we'll digress from whatever this course is. So let's say if I ask you that you have a string whatever, let me not do E, let me just keep, let's say this is what it is. Okay. The question in front of you is, I want to, so how many bytes this is taking, assuming that each letter is a byte? 3, 8, 11, right? So this takes 11 bytes. Now, can you help me reduce the space taken by this? I want to compress this. So I want to design a very simple compression algorithm. So for example, so I can simply say this becomes something, this becomes something. Okay. So what is my vocabulary here? Which letters are appearing? So I have A, B, C and nothing else. Okay. Now assume that we still have English vocabulary from A to Z. So what is unused here is from Z onward and D onwards to Z. I can call this Z, this can be Z, this is still A. So the whole thing will become ZZA and will take only 3 bytes, or am I wrong here? This will take more because you also need to tell me what is Z actually, right? See, if you just give me ZZA, the information is lost that Z was actually equal to AA, so triple ABC. So you need to also give me the fact that Z is equal to, this makes sense? Okay. Now, as the name suggests, byte pair encoding. So this was an algorithm given in 1994, and since I have not brought that paper, I don't remember the name of the author. Okay. But this is an old technique and it was done to compress the data. Now this is byte pair encoding, okay. So this is not allowed directly as such, okay. What you are supposed to do is maybe, so you can, let us say, combine these bytes. Since it is byte pair, so you can combine the adjacent pairs. So let us say this guy becomes Z, this guy will also become Z. So what is my resulting thing? B, C, so assume there is no space here, Z, A, B, C, A, is that right? 4, this is fine, okay. Can I still merge? ZA, ZA, so can I still merge? Yes. So let us say ZA now becomes Y. So this whole thing becomes what? Y, B, C, Y, C, A. Can I still do something? Note that we are doing for byte pairs only. Sorry? Right. So let us do that here. Yes, you can do that, okay. So I am just doing it one by one. So let us say now instead of doing BC, I can do YB. So YB, what does this become? X, XC, XC, A, and now, so this is WWA, which is same as my, but in this case now Z will be equal to, so there is no Z, W is equal to XC, and now X is equal to YB, and Y is equal to ZA, and Z is equal to AA. What is being achieved here? You are given a lot of text, right? Now if you do this over a big text, and if that text was taking, let us say, 1 GB, you think it will end up taking something like 500 MB, 400 MB, because you have roughly halved. I mean, there is nothing special about this half, right? But assuming that you have merged a lot of two pairs, you will roughly end up taking a lot lesser space compared to the original text, right? Agreed or not? This is simple, right? Because see, here my string was very small, so this information is significant and comparable to that. But if you have a text of 1 GB, this kind of information will be negligible compared to your full text, full corpus. Now come back to our course on LLMs. The same idea, byte pair encoding. So we call byte pair encoding tokenization. Now these are the things we have talked about in the past as well. Large language models, they have been challenging our understanding of the languages that we have designed ourselves, okay. So deep learning models, they don't care about syllables, they don't even care about words, as we know, right, because they don't break words at the boundaries we are used to. They don't break sentences at the boundaries we are used to, right. So when we saw BERT, we saw that sentence there means any contiguous chunk of text starting from somewhere to end somewhere. The only condition was that it must be contiguous, that's it, okay. So it does not have to follow the structure of a sentence as we have been studying, as we have been knowing until now. Now, so what happens in this tokenization? Now, so let me start, because I don't think I have that much time today. I want to finish this today itself. So what are the possibilities? So if you are given a big corpus of 3.5 billion words, okay, what do you think will be the vocabulary size? 500k, 1 million, it will be a huge one, right? And what's wrong with this vocabulary size if you are doing language modeling? My question is, if you are given a big corpus of 3.5 billion words, my vocabulary size may be something of this kind, 500,000 words or 1 million words, unique words. What is wrong with keeping this big vocabulary? Space, one thing. What more? So space, why space? In which sense space? So my embedding matrix will be of size 1 million cross 768. So 1 million cross 768 means 768 million parameters just for embedding matrix. What else? Assuming you have space, what are other issues? Huh? So processing time will also increase, but can you pinpoint that one thing where processing time will actually hurt you? You can. Softmax, right? You will be computing a softmax over 1 million tokens every step, because that's what you do, right? This is a very big challenge. So how to take care of that? So if you reduce your vocabulary, you don't just reduce your number of parameters, you also reduce the computational cost significantly each time step. And now compare the vocabulary of BERT, which is roughly 30k, 35, so 30522 tokens compared to 1 billion now, 1 million now, sorry, okay. That is a 30 times improvement, huge deal. So BPE is used by which LLMs? So this is used by GPT-1, GPT-2, GPT-3, and I don't see any reason why GPT 3.5 or GPT-4 are also not using this, right? There are papers that say this is not the optimal and so on, but who cares, right? Because see, once a thing has started working for you, you won't like to change those things. You change and then you realize something else went wrong, right? So from what I know, all these starting from GPT-1 to GPT-4, they use BPE tokenization. Now on the other hand side, you have what was that name? BERT. So GPT-1, 2, 3, until here I know, 4 I am not sure because nobody knows what 4 is doing. But I would assume this is still the same. Now there is another tokenization algorithm called Wordpiece tokenization. And that is used by BERT. Significantly, it is just BERT, Google based thing. This now the problem here, as you can guess, there will be not just these two, there will be many more. So there is something called sentence piece tokenization as well, but it is not used by those well known LLMs. There are LLMs that use it, they are famous, they come from Google, Meta and all these, but not as famous as like everybody knowing them. Alright, so we start with this now. So we first take BPE tokenization. So, let us say if my corpus is so this example is directly from Hugging Face course on NLP and chapter 6, there you can look for BPE tokenization. Okay, write this down, Hugging Face course on NLP, chapter 6, BPE tokenization. So, assume my corpus has this. Now, BPE as tokenizer was introduced in this paper, neural machine translation of rare words with subword units by Rico Senerich, Barry Hedo and Alexandra Birch. Okay. So, paper was published in 2016 before transformers actually came out. And transformers also use BPE, if I remember it right. Okay. So, you have this, and now we are also saying that Hugging Face actually appears once in my corpus, Hugging appears one, Face appears once, Hug appears once, Hugger appears once, Learning appears two, Learner appears two, Learners appears 2 times, and Learn appears 1 time. So, this is input to your BPE algorithm as it is provided in the paper I just pronounced. Okay. Pretty famous paper, cited more than 8,000 times. Now, this is my corpus. Okay. How do I tokenize this using BPE? I will be running an example of this. So, now it is difficult for me to draw exactly everything that they have done here, but I will try anyway. So, what you do is you split this, all these words, or even if it takes time, it is fine. You split these things character wise. So, help me do that. H, man, this is going to take a lot of time. Fine. Okay. Now, so this is input to us, corpus. So, you take your corpus. So, for example, if you are talking about GPT, what will you do? Take corpus, list all the unique words that you have, and also list their frequencies. So these are their frequencies. Everybody is fine with me until now? Okay. Now you break everything character wise. Okay. Now, so we have already in pre-processing, we have already isolated, dots, all the punctuations. Okay. Now, so this is fine. Now you take byte pair. So you take pair frequencies now. In fact, let me just write it here. So this is the corpus we have written. What is this guy? This is, let us call this splits. This is my splits, and these are my pair frequencies. So we need to compute pair frequencies now. HU, just pair, we are not going until 3 bytes. HU, so I have H plus U. What else? This is again going to take a lot of time. U plus G, so HU is here, I shift, U plus G, then G plus G, and keep on giving me. So G plus I plus N, N plus G, G plus F, F plus A plus C, and then C plus E. एक ही word हुआ है यार अभी तो. So 3. Okay, but I have that side of port too. So fine. What more? HU is, I have HU there. Anything repeated in this until now? Anything repeated? In this, anything repeated until now? No. I see HU. Do I need to write here again? No. So I can simply write here. So let me write just 1, 1. All these are 1 until now. Next I come here, I see HU. I don't need to start a new one, I can simply write plus 1. Next, UG. So UG में I just do plus 1 GG plus 1 GI right. So I plus N and N plus G, right? And then GF is not there, so we are done. Next. So FA plus 1 and then plus 1 plus 1. HUG, so HU again, so plus 1. See, I am doing it here assuming you guys are doing it too. है ना? हाँ. Else I could have just shown the slides. हाँ. Next is UG. हाँ. But I can't shift too much. So last guy was learn, just learn. Okay. So fine. These are frequencies that we are counting. By what next? I am done until what? Okay, now come back to Hugger. So plus 1, plus 1, plus 1, GG is also plus 1, GE, this is a new pair, so G plus E once, ER new again, E plus R comes once. This is done? Okay. So maybe I can use, this space. So LE, L plus E, that becomes 1, E plus A, that becomes 1, A plus R, okay, R plus N, IN, have I seen it before? IN, I have seen it before. So this becomes plus 1, NG, I must have seen it before. So this one, so which learning is also done. Learner, I will be mostly updating now, okay. So LE plus 1, EA plus 1 plus 1 and RN plus 1. So are you okay how to do this?
Yes, sir.
So then I can just update the correct answers, okay. So this is 4, this is 4, this is 3, this is 2, this is 3, GF comes actually once only, FA is 2, AC is 2, so we have almost completed until here. CE 2, GE was once, ER was, so ER up, we have started changing it, and LE is how many times? Can you tell me how many times LE appears? I don't need to do all this. 4? Everybody agrees? 4? 7. 2, 2, 2. Okay, and then 1. So 7 times. EA, 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 7. What about the next? AR? 7, right? Now what is remaining is N plus I is 1, N plus E is 2, and R plus S is once. N plus I should be 2. And you will find mistakes in this video too. R plus S 2 times, you are right. Any other mistake? N plus E becomes 4 times. Both Ni plus Ne. So this becomes 4, this becomes 4. Any other mistakes? This is fine. So we are done with the first step. Okay, what is our vocabulary until now? So maybe I'll steal this space for that won't do. So I'll steal maybe this space for vocabulary. Let's see if this works. What is my initial vocabulary? How many distinct letters do you have? H, U, G, I, N, F, A, C, E, R, L, S. So this is my initial vocabulary. Remember, you always see, you can generate text word by word or character by character, right? And character by character computationally you see this is super easy, because how many characters you will have? If you are talking about just English, there will be no more than ASCII number of characters. Okay, so I mean 26 small, 26 capital, numbers, punctuations and all this, they don't give you more than 256 numbers. So you know, such a nice thing, my input will be of size 256 cross 768 or whatever D model is, and I will be doing a softmax over only 256 entities, super easy to do. What might be the downsides of it? See, what is wrong with if I keep whole words as vocabulary? We have talked about, but there is additional problem, which is if tomorrow some new word comes up, your original vocabulary will not be able to, I mean, come up with that one, right? You have to add that word here. But character level, you don't have that problem at all. If tomorrow, until some new character comes up in the dictionary, right, which is much less likely compared to a word, you are fine. So if you are generating at a character level, you can't have unknown words. This way of doing it gets the best of both the worlds. So, right? All right. Now coming back to this. Now, so even though I have not talked about the problems with single character generation thing, but it does not belong here. So fine. This is my vocabulary. Initial vocabulary is just the set of characters. So these are my tokens to begin with. Now I need to keep on increasing them. Okay, how do I do that? You have computed the pair frequencies. You scan from top to, I mean, you just look at this list. So this is kept in a list. If you go and look at the Python implementation of this algorithm, in the same page they have also given you the implementation of the algorithm. Okay, so you scan this list. The very first thing that you encounter, which is so highest. So this gives you the highest, right? This is how they are doing it, right? So number 7 is the highest. You choose that thing. So this guy becomes my new vocabulary now. I mean, I have original vocabulary this, LE gets added. So LE is a separate token in itself now. Okay. And once you have made LE a token, what else am I supposed to do? Once you have made LE a token, what else am I supposed to do? So wherever you see LE, where do I see LE? once, twice, actually 6 times, and then this 7th time, right? They all become one thing now. So whatever was, character based segmentation, it now becomes this whole thing because LE is here now. See, this step is important. You look at these byte pair things, you look for which one appears the maximum number of times. Now there is a tie here, so you just choose the first one. So you chose the first one, there goes 7, LE becomes a separate token in itself. So I add this to my vocabulary list. Write this down if you are writing this everything. So I add LE to my vocabulary. What do I do next? Once LE is added to my vocabulary, I adjust my splits. So now this whole thing becomes one token. Now where will, so am I supposed to remove L and E from here? So write this down, you don't remove anything from your previous vocabulary, you only add, okay. So these are called merge operations. This making of LE from my previous vocabulary, that is called merge operation. So you have LE here now. Not corpus, you will keep on increasing the vocabulary size. And how many times you merge is basically depends on how much vocabulary size do you want. So let us continue. I have this one. What do I do next? This guy goes away. LE should go away, right? So this guy is out of my list now because I have merged both. There is no L plus E anywhere anymore. If I call LE some Z, right? There is no LE anywhere. Everybody agrees? So this we just drop. What do we do now? Repeat the same. Sorry? हाँ. No. See, the thing is, you are not dropping everything. You are dropping just what you have merged. Okay. Next, what happens? No, see, what you are saying is true, but this whole thing needs to be seen here. What you are saying is true. EA will no longer be here. What will be here? So you need to take a snapshot of this now, right? Because what I am doing is the next step. There is no EA as such, but what is there? So I need to come up with something new. What is that new? LE plus A, is that a new? So everything else remains the same, but LE plus EA, that needs to be added here because LE is my new vocabulary. So LE plus A needs to be added. So I will just, where should I do this? Here itself. So LE plus A, how many times? 7 times. Okay. You don't see EA anywhere? No, if you don't see EA, see, we are doing this inside a loop. You started with the vocabulary, it was this, you split according to vocabulary, you counted these pairs. Done. Once you have counted these pair, take the max of it. If there is a tie, take the first one. Merge it, bring the merged one here and redo this whole thing again. So we are just doing everything from scratch. This is my vocabulary now instead of just this, right? So if there is no EA, what do I do? In this fresh iteration, so I start doing it again. This whole thing remains the same. When I come here, this is a token in itself now. So LE plus A, and that gets counted how many times? 7 times. Do I get E plus A anywhere? No. So then I simply don't have it. I hope I am doing it right. Yes. Okay. What next? So we are done with this new thing. Now I need to go over these frequencies again. So go over them again. Which one is highest? 7. LEA occurs for the first time. So LEA now becomes here. Okay. And I'll choose a different color. Guys, what is the time? Huh? So this becomes here. Is this fine? So is this fine? So A plus R, LE plus A I had. So now what will come? Everything, this guy, we are not touching this one at all. We are touching from here only. A plus R goes away. A plus R goes away because there is no A plus R anywhere else. Okay, it was only 7 times. So this guy goes away. But what comes in? L E A plus R, and that appears 7 times. Do I need to adjust any other thing? I don't think so. Okay. So L E A plus R, what will happen next? Look for max. This guy goes away, right? Nobody asked me to remove this. So what comes? Again max is LEA plus R. What do I do? So and what do I add here? LEA R. Okay. So what do I do next? What do I do next? LEAR I have added. So if LEAR I have added, this guy goes away? Yes. This guy goes away. So this one, am I at the fresh start of this iteration? Okay. So this is my vocabulary. I redo this whole thing again. I scan from here, highest is R plus N. So in this case there is no tie. So there is no tie to break. R plus N. What do I do next, guys? Right. That is what I was about to say. So what should I do? LEAR plus N equal to 7. Right. So now this happens. This is the only one with the highest one. So what you have here is, okay, All right, so we are done with these merges. Now what next? So if you start from, I mean, highest is 4. Wait. Sorry? Here? That I have added there. Sorry? यहाँ पे? So I have learn plus I first, but before that tell me, so just let me see the frequencies now. 4432, 4432, 33, they say this is 44 now. Is this 44? दो बार ICIN, okay, 4, right? So see, I mean, they are also continuously making these mistakes. So this is 4, this is 4, so NG is 4, GF is 1, FA is 2, AC 2, CE 2, GE 1, ER is, ER they say 5. So ER and ER is 5, right? So ER is 5. Learn plus I. Learn plus I. Is that right? Yes. So learn plus I appears 2 times. And what else? Learn plus E. Are you sure? 4? 4. What else? And the last, so learn plus I, learn plus E, that exhausts here, and that is just learn. Okay, so that is fine. Huh? N plus I, E plus R. So you take max is 5, max is 5, so that is just 1, there is no tie to break. So what do you do now? ER. So I add ER here. What goes away is, so now first let me mark ER. ER, anywhere else? ER. Okay. Guys, what do I do now? This is fine, this is fine. What is not fine? देखो, I have lost the track of it now. You have to help. So, okay, so let me put it this way now. You keep on doing this, you keep on, so where do you stop? No, you decide I want 30,000 tokens. So for example, I could just stop here, I could have just stopped here by saying I want 5 more tokens. So you run merge 5 times and you are done. But this was a super small corpus with just maybe 2 words, hug and learn, right? So you had all these pairs. I mean, this particular toy example was a good one, because else this would have been a daunting task for us to do, and that too repetitive. Okay, so you repeat this just to reach the vocabulary you want. So if you want to reach 30,000, do merge such that you have vocabulary size equal to 30,000, 40,000. That way, from what I know, GPT-4 has vocabulary size of 100 256, so somewhere around 100K, okay, and GPT-4 as well. So you keep on doing this. Vocabulary size will keep on increasing, and you decide how much vocabulary size you want to keep.
So sir, that vocabulary size is equal to the token size. Number of tokens.
Vocabulary size equal to the number of token size. These new things that you are doing, yes. So your vocabulary is no longer unique words, it is this. So unique words here were 1, 2, 3, 4, 5, 6, 7, 8, 9, right? And their frequencies are also listed. But you started with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So initially your vocabulary size was 12, number of unique words was 9, and then we processed to change it. So you can keep on doing this, and so just this. If you have a sentence now, let's say, so now if you have just this one word, how will you tokenize this? So then we'll see, finally they have, so finally we have done just until ER. Listen, finally they end up doing this. So this is the final vocabulary after they ran it for maybe 8-9 times. Okay, tell me, how will you tokenize this now? So this is your vocabulary. Shall I tokenize it like H? So let me, after this I'll leave you. So shall I tokenize it like H, U, G, S, like this, all 4 different? Hug plus S, why so? No, but I also have H, U, G, S, so I can tokenize it this way. I also have H, U, so I can tokenize it this way. I also have hug, so I can tokenize it H, U, G, S. Why did you go for this one and not this one, this one? See, there is something called longest match, and longest match is everywhere in computer science. In computer networks, when a router is looking for a particular IP address, it does the longest prefix match. Longest match is everywhere in computer science, and that's what you are doing here. Because if you were to take these tokens, why do all this mess in the first place? So you are now learning embeddings for these tokens and not for words. And that is why I am saying, you know, these large language models, they are saying we don't care about your understanding of language. That is wrong. Because what you call words, I don't call them words. What you call sentences, I don't call them sentences either. Okay? So one more minute and I'll be just done with one more thing. BERT uses something called Wordpiece tokenizer. And Wordpiece is exactly the same, just that in this one you were computing these numbers based on frequencies. There you compute scores. Okay? And what is that score? So the score is frequency of the pair. So again you will draw this table, frequency of the pair divided by frequency of the first character into frequency of the second character. Based, so write scores, these scores, okay, and take the max score and repeat the same thing. Okay, that's it. Now, that is it for today's class. Tokenization is over.